adaptable, plastics provide safety, comfort and convenience in many aspects of everyday life. Precisely engineered products like multi-layer packaging films and fibre-reinforced thermoplastic composites combine the useful properties of different materials in ways that a single material design can't always match. Once their useful working life is over, however, these multi-materials present a particular challenge to current recycling methods, since they contain different plastics, polymers and other materials intimately bound together. It's not possible to separate them using established mechanical sorting approaches. Partners in the MultiCycle project from across Europe have collaborated successfully to address this challenge, demonstrating for the first time an integrated industrial pilot facility for selective recovery of single polymer recyclates from post-industrial and post-consumer multi-material waste feedstocks, bringing together several enabling technologies. The MultiCycle pilot plant combines advanced spectral imaging with AI-driven advanced process control methods to monitor the composition of the incoming mixed plastic feedstock and ensure that the core polymer selective dissolution technology at the heart of the process is operating optimally for the materials it is receiving. The complex spectral information obtained from either near-infrared hyperspectral imaging for flexible packaging waste or laser-induced breakdown spectroscopy for composites is interpreted by the process's control software to determine the best strategy for recovery of target materials. This consists of one or more dissolution steps, depending on the number of target polymers for recovery, with the recovery order determined by the thermal and solubility properties of the polymers. The MultiCycle approach has been demonstrated for a range of commercially relevant plastics, variously incorporating polyethylene, polypropylene, polyamide, and PET. The process allows recovery of near-virgin quality single polymer recyclates under moderate thermal conditions, using environmentally benign solvents, which are recovered in closed-loop fashion within the process for further cycles, and without recourse to chemical depolymerization. The recycled polymers obtained can then be reintroduced in truly circular fashion back into the value chains for manufacture of new generations of value-added, high-performance, plastic-based products. With all the concepts proved and invaluable experience gained on a representative, integrated pilot-scale industrial demonstration, the MultiCycle process is well set to take the next steps towards commercialization.
Yeah, thank you, and thank you very much for providing that very impressive video. And John and your team, thanks. Really a very nice one. It's also very fresh, I think only 2 weeks ago that it was finalized. Yeah, now we will talk about the progress made in MultiCycle, and hopefully that works. No, it was also a bit too fast. Let me very quickly start with challenges and what we were starting with. And we have two fields. We have the automotive sector and we have the packaging sector, and we will start with the packaging here. And that, in the end, more or less two different waste streams we are tackling here. The one is the post-industrial one. So companies like Amcor, like many other film producers, have, in the end, waste of, let's say, these multi-layer films. It is not too much, of course. They are very effective in producing that. However, there is waste. And such a waste is not really welcome, let's say, in the waste industry, since it is then a composition made of, in this case, polyethylene and polyamide. And it is a mixture. It is directly fixed one film to the other. So no real mechanical way of doing anything with that. Therefore, it is not easy to bring that to waste managers for money. Sorry. It's very sensitive, that one. Does not like me. Probably you can help me and just go one slide back. The other way, yeah, thank you. this one is probably the most important one. It is the flexible packaging post-consumer. This arises in many different sorting facilities all over Europe, where we have, let's say, intact waste management. However, it is not like the solid waste sorting that we all know from NIR sorting, which is then the more or less pure PE or more or less pure PP. In flexible packaging, the challenge is much higher since sorting doesn't work that well. And that means we have waste streams like that. It is not only containing the multilayers. So we are always talking about multimaterial waste streams. It is not sorted out as one fraction. However, it is part of that one and complicates recycling of these fractions. So there is not a very high yield. This is exactly what Peter was telling us a few minutes ago. It is a high challenge to make very valuable, high-quality material out of this one. And this is what we're addressing here in the project. Let's try that one. And this is why we said for the packaging, it was the challenge to try to get high-quality PE, PE, PA, and PET out of that one. And the one idea was to bring that back into packaging, but there were also the idea, if that's probably not good enough, to go back into textile fibers. Oh, again, went too fast. Oh, yeah, thanks. In Automotive, this is just what I found in a publication from 2013. Here we see that the composite application in Automotive, and this is here shown for BMW, Nissan, Daimler, Audi, and Porsche, whatever, many different brands are using that in many applications all around a typical car. And of course, all these applications increased since then. But this is more or less probably a car. So that study is almost 10 years old. So this is something which may now arise in waste management. And of course, here, once again, the challenge was to get the material out of that. And we focused in MultiCycle on the P and the PA, and of course, also in the fiber reinforced materials of that with glass and carbon fibers. And the idea was to bring the polymers and the fibers back into application. You see there's probably some more materials in here than you will find reported later on, since this is then the difference between what we did in the very beginning as a very broad approach to check what is feasible, and we concentrated in the end more on the materials where we had the highest interest and the best results for, like for PP and PAs. The technology, so I guess it was one before. No. Can you help me, please? Okay. No one, next one, okay. The solution that we have in mind is the so-called physical recycling using solvents. It is a solvent-based technology. We call it the CreaSolve process, which is part of the material recycling family. And this is, for me, very important to distinguish this one from the chemical recycling, which goes back to depolymerization or to feedstock syngases, as Peter told us earlier, since, of course, if you go back to monomers and have to start repolymerization, this is really energy inefficient in the end, and this is then resulting in low performance in LCAs. We don't go back to monomers, we keep at the polymer level, and that helps us to save that energy, and this is why we are really also energy-wise and LCA-wise comparable to mechanical recycling, but using the solvents we are able to produce more pure material, and we are able to make use of feedstocks which are not suitable for mechanical recycling, since we have, let's say, the cleaning step integrated into that process. How the process works. One step back, please. Okay, how the process works. This is quite easy. We start with having a waste stream, and we define what is the target. The target may be an ABS, a polystyrene, a PE, PP, whatever. Every kind of thermoplastic in a waste stream we find suitable or we would like to get back. This is then dissolved in a very specific solvent. And in this stage, purification is much easier than in the melting stage. We have very comparable low viscosities. So any kind of filtration is much easier. We have even a chance of being extractive, using an extractive cleaning. So that helps us also to remove compounds, chemicals, which are not liked. So some of the ones Peter was addressing from the printing inks, degradation products, or whatever. So these can also be purified in the process. After that, we have a drying step. Of course, we need to get back the solvents. It's not useful to waste all the solvents that we use in that process. It is totally recovered here in the solvent reconditioning. And when this is working, then we have a recovered polymer. It is then a pellet. It's not a powder. It's really a pellet, like you all know normal recycled materials, and it should behave like that. Here you see what comes out from purification is residues. So sometimes this residue is just used for, let's say, incineration. It may also be used for a second cycle. So this is the multi-cycle approach. We start with a, let's say, multi-layered waste. We just go for polyethylene in the first round. Then this residue is taken back into the waste stream, going for polypropylene, for example. And then the next one could be a polyamide, if feasible. Technically that's feasible. We, of course, have also to calculate if that's economically feasible and makes sense in the end. However, this residue can also be a fiber. In the automotive industry, we used post-industrial PP glass fiber and PP carbon fiber materials. Here, the residues were nothing to get rid of. This is, again, a value if you consider, for example, carbon fibers here. Important, this is a very general approach. It is applicable to all thermoplastics. The solvents that we are using, they're specific and they're safe. Safe in terms of industrial usage, but also safe if there's probably a low ppm level left in the products. There's no issue of that, since it is a green solvent, let's say green or a safe solvent in terms of toxicity. It helps us to get rid of the impurities and contaminants, and in the end we have a final product free of foreign polymers, free of these impurities, and quality-wise, it should be and is competitive to virgin. When we started, I hope it didn't switch one. When we started in 2018, we had of course, developed that for a few years. So we started in 1997 with the first trials in dissolution-based recycling. So in 2018, we had that running, and we also knew that it's feasible to use that process for many different waste streams and polymers. But it was all done in lab scale, or in this, let's say, small technical lab with vessels of 100 liters, or here probably a bit larger ones. We had one successful upscale in Indonesia, where we could show that it works also for PO recovery from landfill materials, but it was only going for one target polymer. So it was not a versatile one. And that was then the situation that we had no other demonstrator plant available for all the other polymers and thermoplastics that we promised that we do so. And you can imagine that this capacity of a few kilos per day is not very significant if we want to roll out such a technology on a global scale. Therefore, we are very keen on products like MultiCycle, who helped us to come a step further here. And of course, this ended up in that we had no technical scale production of recycled materials from multi-layer packaging or from fiber reinforced materials, of course. And the objective that we then had is to engineer a pilot plant as a versatile demonstration capacity. It's useful for automotive and packaging. So in the end, if you're a chemical engineer, you know you have to concentrate. You really have to know what you do in such a plant. This one is a versatile one. So whatever we do, it was a compromise between, let's say, a 60% post-industrial waste stream from flexible packaging, or another one, which is a very defined PP, glass fiber, carbon fiber one. You need to, in the end, a complete different setup of processes. But it should be a versatile one. And of course, it is not only building that one, it's also operating this. Since in the end, if you have this car, you need kind of driver's license to execute all these trials on that one. And of course, we also had to learn to use that new facility. And in the end, we had then to cooperate with all the partners like Amcor, like Tofaş, like TAF, Farplus, Ceylon, and the other partners here in the consortium to tell us what they think about the qualities, what they think on how to integrate our recycled materials into their products. And that means, in the end, we had, this is a bit tricky. One spec, yeah. We had to bring in our engineering skills here in the very beginning, but also the operation skills. So the same people who were involved in building that plant were now, later on, the operation specialists. And it was not only the operation skills from the engineering team from Lömi, also from our team, who have never done that at that scale. So it was really teaching ourselves with our own process. And in the end, we had to develop the quality skills. Of course, our lab people exactly knew how the product should look like in the end, but we had to teach the people at the plant that it's really exactly that one that we expect. So this was the big challenge. And the good news is, one spec, please. One step back. The good news that it finally worked out. So what we did, just to come back, we used material for the packaging case. We used material post-consumer wise, here PE, PET and PEPA, and we used post-consumer material coming here from the film fraction, which is a flexible packaging waste. And you see, this one is not very much sorted into all the defined streams. This one is really a mix. And comparing and depending on the quality, it may be something with 60, 70, 75% of PE, for example, in there. Next one. And when we started, we had this as a typical result. We got such a post-industrial material. We recovered the PE out of that, the polyamide. We had as a residue adhesives and inks, and here's small mass balance of that. Here we see, I hope you can see, the polyethylene film, which comes out of that. Here you see that in the beginning we had even some troubles with good qualities of PA. That doesn't look too good. Since you see the separation of PA from all this rest is not that easy, but finally also that worked out much better. Next one, sorry, once back. So, and this is now what we can proudly present as a major outcome out of this project. It is the Upscale pilot plant. It is a TRL7 pilot plant. You've seen that also in our large, in small video, sorry. It has a nominal capacity of 25 kg an hour. It is placed in a hall with 800 square meters, 7 meters height. It has a plant floor space of 350 square meters. Just to give you a bit of impression, it has 820 single components and more than 1 kilometer of piping in there. And it is, of course, also in Arctic's, the Arctic's directive here is also fulfilled. What is very important in the end to understand, and what makes the biggest difference to our small technical lab scale workers, if you switch from one material to another, it is not just saying, okay, today it is PE, tomorrow it's PP. It is really taking time to refill all the piping with the new material. So when we switch from one to the other one, we just waste another 200, 300 kilos of the new waste material before we can produce something. This was also learning, not only for us, also for the whole supply chain in the project, that we use much more feed than we can produce as a product. And let's go one step ahead. Sorry, once back. This is the demonstration program in operation that we went through. You see here we produced first post-consumer polyethylene from post-consumer, multi-layer material. Here, exactly what I told you, 100 kg of feedstock, and it's not only the yield out of that, it's also the losses in that production. That in the end, we ended up with 450 kg. Since when it really started to work quite well, we had to switch to the next one. Yeah? So this is also a bit of learning in such projects. If you have so high targets, you have not really time to optimize at that scale. It is really, we had to stop at a point where we're probably not optimized. And this is also important for you to understand. Whatever quality comes out, it is, from my perspective, very good first shot. And even these first shots were performed quite well, or pretty well, but it's probably not the final end of what we can reach. We can go through that. So it's polypropylene from the multi-layers, it's polyethylene from post-industrial ones. And later on, we also had as a residue the PET, and this was also used here together with the post-industrial PAPE materials here in packaging. This is only the packaging program. Let's go to the next one. You see the same one? And here it is, in that corner, it is one of the silent champions here in that room. This is Marcel. I really want to point out. He was the one who was present every day at the plant, who did all the work. He had every waste stream and more or less every recycled polymer in his own hands. He was, of course, supported by the team of Jochen and Max from our side, but we could change bases. He had to survive there for almost 1 year at that plant. Thanks, Marcel. It was a very great job that you did there. And the other good news is that the plant is still existing, and it will persist, and we can make use of that one for further trials to prepare, let's say, the technology for commercial scale. And it's, of course, also the wish and the will of Lömi, and José Fonseca is with us to bring that to the next step right now. It is not only showing that we can do that with 24 kilos an hour, we want to do that in a 10,000 ton per year range. And José would be the first one to contact if you want to go this next step. Let's talk about some of the qualities. That's one too much. Please, one back. Yeah. Just to give you a few impressions. This is the recycled polyethylene from post-industrial waste, and it doesn't look too good, honestly. It is still a bit green colored, but you see it looks quite transparent. And if you look into the films, we have many films here, if you have them as a single film later on, you don't see that color anymore. This is also a PE coming from the post-industrial. Here we left the white titanium dioxide in there. And it was then a very and pretty well-defined quality in the end to be used also quite well in all the performances. Now, please, next one. Here we see some DSC curves, and even with the very undefined material of this multi-layer post-consumer material, we managed to be in the PE almost PP-free. You see that there's some small residues in there, but we didn't find any larger impacts of that one. But this one is really, let's say, the quality from the post-consumer packaging waste. Of course, we don't have that issues in the automotive industry there. We had a PP-only material as a feedstock. For the PP, we also, the other way around, find a bit of HDPE in there. But again, quality-wise, it was, as far as I understood from Peter, quite well doable. Next one. Here see some examples for the PP and for the polyamide coming from PEPA materials. And here you see that we, of course, kept some of the colors in there. So we didn't make it that all the colors go out, but we could make use of that one. So in the end, even if it looks that green, the mechanical performance worked quite well, but Peter will talk about that later. Here again, purities. We have the PA and the PET. And here, please consider, this is not the major material in the feedstock. It was the leftover after having dissolved a PE and a PP earlier. This is really what comes out, which is normally just wasted and just incinerated. We could make very good material out of that one. And very pure. Thanks. Just very short overview on what we managed to do with that on the PET. The PET was, in our case, a bit of a leftover. We didn't really expect too much of that. And we've handed that over to Ceylon. They really, after a filtration step, they managed to bring it into their fibers. And probably if you know how these fibers are produced, they have very, very fine nozzles in there. And it worked. And again, not with 10 or 20 trials. It was really one shot, since they had not only reduced amounts available. They put it into and directly had the chance to produce. And quality-wise, here you see a bit of a difference. They got three different qualities, and two of them were quite good. The last one showed a bit, let's say, what can happen in real time or in real research, that not everything is successful here. So you see that standard deviation of elongation is then only half of that, what it should be in the end. Tensile strength also not as good as it should be. Next one. One back. This is what we produced. You've seen that earlier from Tukpa, just to tell you what my learning was. In the end, they used 30% of recycled PA and PP in these thermoplastic laminate sheets, bond laminates. But we were also told that it's possible to use it at any portion you want. They finally only decided to use 30, since this was then doable without any change in the processing. So if they wanted to do a bit more, they just had to adjust a bit of the parameters. And they felt most safe with the 30%, but it's not a, let's say, the final edge of what is doable here. And what is the other one? The production was successful, feasible without any adaptation to the process with that amount. And the appearance, mechanics, and so are really identical compared to virgin with recycled material. Once back. And here again, same pictures for the battery cases and the door panels. We're really keen to see them physically then. So they're not all finalized yet, but once we have them, we of course will make it possible anyhow that there are chances to see and to demonstrate it also physically. Next one, please. For now, we were almost only talking about technical performance. Now let's have a this is really just a very small look into ecological performance of that process. We have a very rough overview on some key issues of the LCA. It is a very long story and a talk in itself. I will only present 2 or 3 slides on that. We will make it available by another way also to show the whole LCA, but not here today. But here, very shortly, of course, we did it with all the background that you need. We defined the functional units, the boundaries allocated of all the primary and secondary flows, try to make it representative and so on. And of course, we did it according to the ISOs of the LCAs. Next one. And just to explain what we did in principle, we had this foreground data, all the chains were included, including also the collection and sorting at the Milo plant. Then, of course, the solvent-based recycling. And we had a look into different waste scenarios, which was a starting point of 60% of PE only in the waste. Then we had another one with a high PE content, 75%. Then we had a look into the PET as a leftover from recycling PE and PP earlier. And we had the model of this PP glass fiber and PA glass fiber materials. And we also had a look into the production of the flow wraps out of these materials, of the door pocket panel, battery cases, and so on. All these data will be published in this LCA. We will find a way just here very shortly. It is one back, I guess. Yeah. No, sorry. Next one. Okay, thanks. Let's start with this one. For the recycling of 1 ton of PE, we see that we have an emission of around about 900 kilograms CO2 per production of 1 ton, sorry, for the 1 ton of LP waste. And you see that most, or the highest portion of that emission is only incineration of the missing 24 or 25%. The rest is quite fair in here. Next one, please. If you compare that to the alternative scenario, just taking the same waste and bring it to incineration, it is more than double of CO2 emissions coming from that one. So the reduction that we have here in comparison is an emission reduction by 67% by using our Resolve. And here, sorry, this is a mistake here. It should be PET. Yeah? Next one. And for the PET, for example, just to give one of the other examples, it is in the same range. And for most of the other polymers, we are always in that range of around about 800 to 900, sometimes a bit smaller. It is really competitive, and if you compare it to the alternative scenarios of incineration, or if you just look the other way around, not in production of recycles, but also in treatment of tons of waste, we also see a very, very massive reduction of CO2 emissions. So it is not only technically feasible, it is also worth to do it from an LCA perspective. And when then come back to one of the first slides, if you compare that now to chemical recycling, we are on the completely different side of that angle. No? So it's worth to do that economically and ecologically, and also quality-wise. But this will be taught later on. I now hand it over to the other part, now presented by Anna Maria on the PET monitoring systems. Thanks.
Okay, hello again. Well, as Peter commented before, one important part in this process is also the identification of the waste, of the components that we have in the flows. So to do that, one important technique is the process analytic techniques that should be applied in this kind of processes. But what is process analytic techniques? Actually, this is defined as a system for analysis and control of manufacturing processes based on timely measurements of critical quality parameters and performance attributes of raw and in process materials. In this sense, we can think that the process analytic techniques has two main pillars. The first one is to have tools, real-time and inline or online tools, as some kind of technologies or techniques based on spectral methods, imaging methods, biosensor, or others. And the second pillar is the multivariate statistical methods to analyze the data. And in this case, we can think about different techniques, for example, for the design of experiments and optimization, dimensionality reduction, spectral methods, pattern recognition, and other data analytic techniques. But why these kind of techniques are the right ones for as source of information for driving these processes? This is because the PAC techniques can provide, as I mentioned before, the real-time information that is transferable to the manufacturing process. We can avoid risks waiting for lab information if we have this monitoring of real-time. And also, these kind of techniques allow us to control or monitoring the process based on the functional objective of the process, as opposite to supervising and maintaining the assuming optimal conditions based on traditional recipes that you can program or you can set before. So this is because two main reasons. The first one is the availability of the sufficient quantity of information, and this information also is very reliable. And in another hand, we can show hiding information from the data via ICT resources. In this case, we can apply artificial intelligence tools in order to build also decision support systems that are free from cognitive biases and prejudices. So in this case, we have to consider that this kind of advanced process analytical techniques with the artificial intelligence should compromise both in a cost-effective combination. The path techniques on the one hand, and also the incorporation of other artificial intelligence data management tools. If now we focus on the recycling processes, as we mentioned before in the introduction, the standard techniques for monitoring and material identification in recycling processes are currently focused on monomaterials, and these techniques doesn't work very well for multimaterial or complex compositions in the flows. How we can overcome this gap in the state of the art? As I said, the current progress in photonic science, together with this kind of advanced data analysis, implementing different modes or algorithms based on artificial intelligence, are enabling this to bring in practical challenges previously not feasible. For example, in terms of classifying more complex materials that before were not able to be classified properly. So also the couple of PAC techniques and artificial intelligent advanced data management system has also the potential to reach new applications that currently are not feasible. Okay, one back. Okay, so considering this situation, this is one of the main objectives that we have with these techniques in MultiCycle. Apply to artificial intelligence to real-time monitoring system to recognize multi-layer and reinforced plastic waste for the monitoring and classification in the process, in the recycling process. We had different objectives with this development. The first one was to develop feasible in this case online, sorry, prototypes for complex plastics waste identification. Also, we demonstrated that the identification of these complex materials is feasible. Also, we demonstrate that the artificial intelligence can be a complement for traditional models for data management in these cases. We obtain sustainable waste streams for economic processing and specified suitable waste stream requirements. And we did this for both sector, multi-layer packaging and the reinforced composite that they have different compositions in their flows. Sorry. Okay, can you go back, please? Another one? Okay, thank you. This is a photo or a schema of the main or the overall application of the past system overview in the project. Here we were focusing two main points of the process. The first one was in the input. Here we developed two different monitoring systems for the packaging plastic and the other one for the black plastics that they need different, let me say, technique behind to be identified. And also the approach includes the development of a monitoring system for the creasolve in order to provide a decision support tool for the monitoring and performance of the system, of the process. The first case is the monitoring system for the plastic identification. Here you can see one photo of the prototype that we developed and built for the project. Actually, we developed two prototypes. The first one was dedicated for the multimaterial packaging. The first prototype was based on high spectral imaging techniques coupled with artificial intelligence for modeling and data analysis. In this case, we were able to classify different kinds of target materials in the project. In this case, PE, PP, PA, PET, and PLA. And also, we were able to quantify the percentage of the type of material in the flow that income to the process. The second one was dedicated to the reinforced composite. In this case, the technology behind is different. It's laser inductive breakdown technology, which is LIPS, coupled again with artificial intelligence model for the data analysis. And in this case, we were able to classify or to work with the reinforced composite, PA glass fiber, PA carbon fiber, PP glass fiber, PP carbon fiber, based on the carbon fiber and the glass fiber content of these flows. Again, we were able to quantify it in a percentage of the material type in the flow. Okay, now just some general features of these prototypes. The prototypes were all-in-one system. I mean, they had a conveyor module, conveyor belt module to input the material with a feeding system incorporated, and also it brings the control and electrical cabinet, as you can see here in the photo. Here are different photos of the conveyor with the different system to allocate the materials over the conveyor. Also, the prototypes included the advanced data modeling and analysis system software. We developed this ad hoc software platform and control system based on the Pathbox from Iris for the data analysis, storage, and visualization of the operation. Here are some screenshots of the software system. The software can provide different information in terms of values and also in terms of graphics. And also the system allows to export the data into data documents in order to store it, not only to see in the screen, but also to store the data about the composition information. Here are more photos about the visualization of the results, and here are the data sheets of the documents that you can export. Oh. Okay, sorry. The second part, it was the decision support tool for the process monitoring. In this case, this decision support tool included a smart interface that it was coupled with the platform software of the prototypes, and this tool enabled the monitoring and optimization of the dissolution process. Behind of this decision support tool, we find also artificial intelligence modeling based on different input data from the monitoring system regarding the composition of the flows, also regarding some process variable and other data that was included for the decision support. And the results that we can obtain with this system is, for example, to propose a dissolution process setup. Considering the waste input composition, the system is able to recommend some key aspects and values for the processes. And also, the decision support tool was able to perform a deep analysis to support the decision of whether to process or not with the dissolution process according to some criteria implemented behind. Just to mention that some part of this work is also in a patent request. So this is one of the output that we obtain also in this project. And this is all from my side.